Hello everyone. In the last class, we were discussing about parameter estimation using maximum likelihood. These were the key equations that we have arrived at in that whole process. Let theta be the set of parameters that needs to be computed. And in case of maximum likelihood, what it does is whatever you have essentially samples from the distribution. Let those samples be x1, x2, x1 bar, x2 bar, and xn bar. Now you choose that theta which maximizes your likelihood of this theta. So that's essentially probability of theta given this x bar. That's what you would pick up. So argument of theta that maximizes k equal to 1 to n. Now you also consider that these samples are independent. The probabilities of these particular samples are independent some of each other. So you have what you try to maximize is choose that theta for which the product of all these probabilities gets maximized. We have discussed in the earlier classes about discriminant functions. Instead of maximizing this, you could consider a function that monotonically increases with the theta, and then instead you maximize that function because the relative magnitudes are still maintained in a monotonically increasing function. So that's where you have taken logarithm of this. Then to find out the maximum, by assuming that this is a continuous function, you essentially would take a derivative with respect to the parameters theta, right? And then of course, this a product would become the summation here, and this is like natural logarithm of probability of xk given theta or for a theta value. So that this function is with respect to theta, so it's like natural logarithm of some function of theta. So 1 over natural logarithm of x, for example, if you are doing with respect to x, the derivative it is 1 by x, isn't it? So similarly, 1 over probability of xk comma theta into dou by dou theta of probability of xk of theta. Okay, then I have given you a couple of examples. Did anyone face any issues with those examples, or everybody is able to solve them? Maybe what I will do is I will solve for sigma square, which is little more trickier than what it is for solving it for theta. So here what is given is, assume that your probability distribution of your samples for a given sigma square is Gaussian distribution. Then your parameters for this distribution are sigma square, that is the variance, and mean values. Now we are going to compute based on this concept of maximum likelihood estimation, what would be the variance and the mean value. This is what we are going to calculate. Okay, maybe I'll quickly calculate. I hope and I wish that most of you would have already made an attempt towards this. So even if not, I'll do it for one, that is assuming that here the mu value is known and maximum likelihood estimate for sigma square is what you are going to compute here. Okay, that's again, I considered here my feature vector is of one dimension, so that everything is vector calculus, and these vector derivatives I could avoid there and could go with simply the scalar. Now you could see I have sigma square, and of course because of that I need to take derivatives with my theta is now just a simple scalar sigma square. So let me first look at this equation in terms of sigma square for my convenience. So I'm simply writing it as xk of sigma square is equal to, how should I write this? Maybe I'll write it as 2 pi times, okay, 2 pi whole to the power of minus 1 by 2 here into, I'll write it as sigma square whole to the power of minus 1 by 2. Okay, I'm just writing that as sigma square because I need to take derivative later with respect to sigma square. So it's as good as writing 1 square root of 2 pi into sigma square. Sigma square is also under square root, and just I'm bringing that to the numerator, right? And then here into exponential of minus of xk minus mu whole square by 2. This has nothing to do with, this is just a constant, and I have here sigma square then, right? So then, just like I have shown here, I'll use a monotonically increasing function, which is a logarithm. So I am writing now the function like L of sigma square, the discriminant function I am referring by capital L. Okay, this is anyway for one value of k, correct? So I would do it now for all. If I do, that's applying natural logarithm to pi of k is varying from 1 to n, right? 2 pi whole to the power of minus 1 by 2 sigma square whole to the power of minus 1 by 2 exponential of minus of xk minus mu whole square by 2 over sigma square, or x minus mu whole square divided by 2 times sigma square. Okay, so again, natural logarithm of a times b is natural logarithm of a plus natural logarithm of b, and this product would become summation, right? So can I not write this as, how can I write this? Well, I have one term here which is of sigma square, and here another term is there which is dependent on sigma square. So some chain rule I have to use. I cannot avoid doing that. So then anyway, now natural logarithm of a times b is natural logarithm of a plus b. So let me apply on this versus this as two different functions. So then what would happen? So what I have here is this is equal to sigma k is varying from 1 to n natural logarithm of 2 pi, right? 2 pi sigma square whole to the power of minus 1 by 2. Is that correct, or did I make any mistake here? Plus, this minus will come out natural logarithm of exponential. So again, I would write it as minus. Again, it would vary from all values of k. So this would be k is varying from 1 to n xk minus mu whole square divided by 2 sigma square. Is there any mistake from my end? Is that correct? Is everybody with me? Is it clear?
Yes, sir.
Yes,
Good.
sir.
Right. So now what else? How can I simplify it further? This will be equal to minus n by 2 into natural logarithm of 2 pi into sigma square. Do you agree with me? There are n such elements, correct? And this minus 1 by 2, I bring it out, right? Natural logarithm of a per b is b times natural logarithm of a. So that is minus 1 by 2 into natural logarithm of 2 pi sigma square. Such n terms are there. These are all constant. The thing is dependent on k. Such n terms are there. Hope everybody is fine with that. So similarly, minus 1, I could bring 1 over 2 sigma square outside because it is not dependent. Any of those terms are dependent on k value. So k equal to 1 xk minus mu whole square, right? So this is what L of sigma square is there, right? This is, I am here. Now you take the derivative of that with respect to sigma square and equate it to 0. That's how you would get. So in order to get, they call it as sigma square ML, maximum likelihood cap, they keep it. Estimate in order to get that, what you have to do now, derivative of L of sigma square function with respect to sigma square, you do that and you equate it to 0, and whatever you get will give you the estimate for variance, maximum likelihood estimate for that particular parameter, which happened here to be the variance, right? So let's do that. So dl of sigma square by d sigma square, I should write, okay, is equal to, can you help me with that? Minus n by 2 into, what will I get here?
1 upon
For
2 pi
this,
sigma square.
very good. 1 over 2 pi into sigma square. What else do I get?
Into 2 pi.
2 sigma.
Very good, very good. No, only 2 pi you will get, huh? Because your variable here itself is sigma square. If you don't feel comfortable with a variable having square, consider sigma square as something else as some eta value. Sigma square equal to eta. Then you proceed it. Otherwise, it is fine. Right, good. Then what about the next one? Anyway, minus 1 by 2 into, all I have here is sigma square whole to the power of minus 1, x power n, the variable is n into x power n minus 1. So my n is minus 1. So that will make this as plus here, minus into minus plus, x to the power of n minus 1. So minus 1 minus of minus 1. So that will become sigma square whole to the power of minus 2 I will get. Okay, let me write it in the denominator rather. So that would become 1 over sigma to the power of
4.
4. Very good. Anyway, the rest of the term remaining there is nothing to do with sigma. So I could write it right away. Xk minus mu whole square. That is what I have. Now what I want to do is, in order to get the estimate for it, you make this dl of sigma square by d sigma square equal to 0. That means what will happen here, anyway, let me meanwhile just cancel this 1 over 2 pi and this, right? And then what I have here is n by 2 into 1 over sigma square is equal to 1 by 2 into 1 over sigma to the power of 4 into summation of k equal to 1 to n xk minus mu whole square. Well, I could cancel this 2 to this term I would bring to the other end, and that will, and n I will take to the other side. So sigma square equal to 1 by n into k equal to 1 to n xk minus mu whole square. Okay. Now I would in fact better I write it as sigma, because it is a maximum likelihood estimate of this. So I would keep sigma ml cap whole square is equal to 1 by n into k equal to 1 into xk minus mu whole square, right? So as we mentioned in the previous class, this can be used for any distribution. On the other hand, what we notice is typically whatever we are using for computing the mean and variances, you will get the same analytical expressions if you do a maximum likelihood estimate for a Gaussian distribution. That's a good news. And of course, there are some variations. These are, you are computing the mean and variances from given samples. But not the actual distribution, continuous distribution. You are drawing some random samples and doing it. Of course, there is one more expression which tells you the expected value of your sigma square for a Gaussian distribution will be equal to 1 over n minus 1 instead of 1 over n. I'm sure you might have come across this they call it, if I'm not wrong, Bessel's correction that they do to avoid some bias. The reason being, if you are drawing n random variables, your mu, whichever is there, is dependent on those n variables. So in fact, you only have n minus 1 variables there when you are calculating the variance. That's a very a very, I think, a rough intuition that I could give you. Because of that, they would, in statistics, actually, when you are drawing samples, and from the samples, when you are trying to estimate the parameters of the full distribution, they would be using 1 over n minus 1 also. And of course, when n is very large, 1 over n and 1 over n minus 1 would yield you similar results. Okay, that anyway will, if we have to go in much detail here, we have to spend some considerable time with the basics and fundamentals of statistics. But nevertheless, you find it yourself if you are not already aware. Just Google that, and in the Wikipedia page itself, you have a very elaborate discussions and intuitive explanations, even more intuitive than what I have mentioned here. You will find it out. Anyway, for our purpose, this 1 over n expression is good enough. Okay. So in similar lines, now you, this is anyway a worked out example in the textbook. You have another worked out example where they were doing it for mu, assuming sigma square variance is known. The parameter that you need to play with is mu. They have done it. You please do that. Again, for the sake of simplicity, I considered here scalars, and where my feature vectors of one are of one-dimensional size, but you should be able to derive these kinds of expressions for a given distribution. Even if that distribution is multidimensional, you should be able to compute the derivatives and do the stuff. Okay.
Sir, we are currently doing maximum likelihood estimation, right?
Correct.
So, sir, how is it different from Bayes rule actually?
How is it different from?
Bayes classifier or Bayes classification.
Well, see, in the Bayesian classification, we assumed that we know the parameters of our distributions.
Okay.
But we never worried about how to find out how do we know those parameters.
Okay. So there's a
Now
method
what
for
we are
finding those
doing is,
parameters.
right, now what, given some samples of a distribution, suppose what all I am telling you is these are the n samples of class 1. Now what is exactly, and I is here another assumption is that I also know what is the nature of my distribution. Is it an exponentially decaying distribution? Is it a normal distribution, binomial distribution? I know that also here. Given that I know this, how do I find out how do I estimate the parameters of this distribution? This is nothing to do with the classification, but this is part of classification, where in all our earlier classes, barring the previous class, okay, till then we were assuming that we know the distributions mu I bar, mu Z bar, sigma square. This all we know, that is our assumption. But how do we know? That is what we are doing here.
But sir, in this example you took where we are trying to estimate the variance,
Right.
but we can find the variance from the data points, right? Like we can find the
That is
mean from the
That
data
is
points.
exactly, yes, that is what exactly we are doing here. This is
So,
what we
then there's no need for this ML here in this for this parameter, right? Because we can find it directly. So why are we trying to?
how do you directly find we arrived at this expression from maximum likelihood.
Okay.
Oh, and one more thing. Suppose you are already assuming that you already have a Gaussian distribution. Assume that I have a different set of parameters to characterize my distribution.
Okay. Yes, sir.
So then just having expressions for mean and variance are not good enough.
Yes, sir. No, I
Assume
was
that,
just confused for this variance factor because we can find it from the
yes.
data point directly.
Correct. No, that's a very valid and very important point. Assume that I have a mutual, some exponentially decaying distribution, which would be like exponential of minus lambda times x, something like that. So mean and variance will not always completely characterize a given distribution.
Yes, sir.
If they characterize, you could use expressions similar to this and compute it. There are many other possible distributions also. Assuming that you know what is the type of distribution, for any distribution in general, if you want to find out, there is no other way. You have to somehow estimate it.
Okay.
Is that clear? Because that's a very important point that one has to be absolutely have a clear understanding.
Okay. So
Is
basically,
that
we can find it, find these basic ones from directly from the data, but for others, we have to use ML.
right? See, always suppose I have a distribution, I know that there is some distribution, not exactly Gaussian, but I may parameterize it with something else. Where just mean and variance might not be enough. There is something else also would characterize. See, for example, take this simple e power minus lambda x. Mean and variance will not characterize this. Correct.
Yes, sir.
So there are a different set of parameters here to characterize that. That's what this maximum likelihood will give you, a general framework where any parameterized distribution, its parameters can be computed using this.
Okay.
We just double checked here on what is it that we are getting. If it is a Gaussian distribution and if you are computing variance based on maximum likelihood.
Okay, sir.
It is turned out to be same as what you would get a normal variance expression.
But sir, in this variance case, the
Mm.
term variance was in the distribution equation itself.
Mm.
But what do we do when the parameter we want to estimate is not in the equation?
Yes, that is when you will go to. So your question is essentially rephrasing your question. What if my distribution cannot be parameterized?
Not exactly. Like here we are saying that here in the Gaussian distribution,
Mm.
the mean and variance are in the equation itself. We are using the mean and variance in the Gaussian equation, e to the power minus x minus mu upon 2 sigma square.
Correct.
But what if we want to try, estimate a parameter that is not in the equation?
Why do
Some
you
other
then want
parameter.
to? No, why do you then want to estimate that parameter which is not affecting your distribution?
I'm not sure. I'm
No, see, if you recollect, unless you know these parameters, you will not be able to find out the likelihood values and prior probabilities.
okay.
It is for that reason you are estimating them. See, if I have a circle and if you want to compute major axis and minor axis, they are anyway same. It doesn't really matter. It's similar to that. So when when your distribution is parameterized by like say some x number of variables, it is those x number of parameters that you want to compute. You will not worry about the rest.
Okay. I was thinking like correlation or something like that, which is not exactly in the equation directly.
Yeah, that is not required, in fact.
Okay.
See, it is very simple. Your distribution is parameterized with some parameters. And how do you compute those parameters? Given only samples of your distribution.
Okay.
In case of mean, this is very intuitive and simple, and that even a mean of your samples will be also the mean of your distribution. Not every parameter will scale down like this.
Okay.
Here, the variance of your distribution may be also the variance of your samples. If you compute across all the samples that you have, that will be same as the variance of your distribution, almost. Not exactly, but almost.
Okay.
So then things are fine. But this scaling will not always happen. So given samples, how do you estimate the parameters? This maximum likelihood estimation is one such framework that facilitates us doing this.
Got it, sir.
Sir, can variance be zero?
Yes, why not? See, if all samples have same xk bar, then only means then it is actually not a Gaussian distribution. Variance can be zero, but that is no more a Gaussian distribution then.
For this case, sigma square can be zero.
Yes, it can be zero, sigma square, but it will not happen for a Gaussian distribution. Is it not? If you have a Gaussian distribution, what does that mean? You have samples spread across, and it is your sigma square that is giving you. If all your samples are same, that's when your xk will be same as mean. Otherwise not.
So sir, if we are given two variables and we
You
both are
mean
Gaussian,
just to be technically correct, parameters, I think you are talking about.
no, sir, two random variables, let's say with
Okay.
two observations, let's say two set of
Okay.
observations.
Two samples, x1 and x2, let's say, right?
Right. So, I mean, we are observing two phenomena, let's say,
Right.
which is x1 and x2, meaning we have around 1,000 samples for x1 and 1,000 samples for x2, let's say.
Oh, no. What you are saying is then your feature vector is two-dimensional. That's what do you mean?
Yes, sir.
What you
Yes, sir.
mean here? Okay,
Yes, sir.
so let me call this as x1 bar and x2 bar. Each is 2-dimension, right?
Yes, sir.
Okay,
So
yeah. Now tell me.
I'm asking that can we find the covariance through this MLA
Yes.
maximum line?
Yes, you do it as an exercise. It follows exactly in similar lines, except that your derivatives and all, you need to do it a vector calculus or vector derivatives there, where you take the derivative sigma 1 square, sigma 1 2 will come, and sigma 2 square kind of stuff will come there.
Okay.
It will boil down to the covariance matrices that we have discussed about. Please work it out, and you can find out some examples also in the textbooks. You can definitely do that without any problem.
Okay.
And that's in fact, you will come across such problems also. That's a very common problem, no? Because otherwise you have to always satisfy with just one variable, right?
Yes, sir.
I think even those guys, whoever are having an assignment, have a similar thing. Programming assignment was given. So there they were having a very similar thing. But again, what would happen there is, if you assume that your feature vectors are independent, if you assume that your feature vectors are independent of each other, if you remember the
Yes, sir. The
covariance
covariance will
matrix,
0, right?
correct. So that case, you have to simply compute sigma 1 square and sigma 2 square. Then this will be sigma 1 2 will be equal to 0, which would be essentially xk minus mu. If for the first one, if you call it as mu1, something like this you will be getting. We have done something like this earlier. So yeah, mu transpose times mu, these
Yes,
kinds
sir.
of
X
expressions
minus
you
mu
will be
into
getting.
x minus mu transfer. X minus
Correct,
mu
correct.
transfer
Some
into x minus.
correct. Such expressions you will be getting here. You would be arriving at very similar expression even if you do using maximum likelihood.
But in that case, we'll be taking joint PDF.
Correct, exactly. That's right. So good. Then I'll mention few properties of this this ML estimate. So one important desirable property is, and which this ML estimate possesses, is ML estimate is asymptotically unbiased. What does that mean? Is asymptotically unbiased. Any idea on what does that mean? So let me write that here. Expression, mathematical expression. With that, things will become clear to you. Limit n tends to infinity. The expected value of theta of ML hash or cap will be equal to theta naught. Okay, where theta naught is a true value of those parameter. You are taking samples, n samples from that particular distribution. You are randomly taking n samples, and from those n samples, the maximum likelihood estimate you are getting could be theta cap of ML, this one. So the average values, if you are repeating this experiment for various sets of these n samples, right? From the distribution, when I am drawing n samples randomly, I assume that I am 10 times I am drawing n samples. Suppose just consider one variable. Okay, assume that it is just a mean value I am looking at. Actual mean value is 100. Then what kind of things you could get here is, for one set of samples you might be getting 110. Okay, I'm not sure that much will be there. 100, 90. If you are getting something like this, then on an, if you look at the average expected value, that means the average, if you look at it, then this would be unbiased. You would eventually arriving at the same average value. So the expected value of theta of the ML cap that you are estimating will be same as the original theta naught. This would happen as n tends to infinity. So this is unbiased. Unbiased to what? Unbiased to the samples that you are drawing. Okay, that's one important desirable property that this maximum likelihood estimate possesses. Next one is this ML estimate is asymptotically consistent. Is asymptotically consistent. What does this mean is one way of expressing this mathematically is as you draw infinite or very large set or number of samples, and from that you are when you are estimating, and let's call that estimate as theta ML cap, and you subtract that from theta. Note that this can be a vector, right, or matrix in fact. Then this different norm of this being less than or equal to a small value epsilon, that probability will be equal to 1. So this approaches this theta ML cap. If the probability of the difference, norm of the difference less than or equal to epsilon is very high. Okay, so this also tells you the numbers. For example, if 100 is there, okay, for 100, if I am getting 90 and 110, these in fact it also tells you that these also will come very close to actual values. The average value is same, but the distinction, because that's where for a given set of n parameters you are comparing, as n becomes large, how close each individually will be there. The earlier one is telling you the average value of that parameter. Here it is telling that the absolute value, when you compare each individual parameter in that vector with its actual values, these are pretty close. That's what this expression or this property is telling you. So this is asymptotically consistent for any set of parameters that you pick. Then third, so this actually, before going to the next one, you could alternatively a strong condition also, you could say a little bit strong condition than this, you could say is limit n tends to infinity. Here the expected value of norm of theta ML cap minus theta naught, okay, this whole square, this is equal to 0. It's a little bit stronger condition. Maybe your n value should be relatively much higher than to achieve the first one, because there you have given some epsilon value, and with that epsilon, as long as the in terms of probabilities, the difference becoming less than epsilon is the way you are looking at it. On the other hand, here you are looking at the expected value. That's what you are looking at. This is also will represent the same or translate that consistency into your mathematical formulation of the same. Okay, so the third desirable property is ML estimate is asymptotically efficient. Is asymptotically efficient. What does it? Efficient means efficient that, in what sense it is efficient is that it achieves Kramer-Rao bounds, C-R-A-M-E-R, Kramer-Rao bounds, Kramer-Rao lower bounds, in fact. What does this mean is essentially, you could also not only say, so just to tell you very intuitively, as n tends to infinity, you can guarantee that the errors that you obtain is within a limited, this is the maximum error, let's say some 5% is the maximum error that you will get as long as your n is large. So these kinds of bounds you can establish, so they are asymptotically efficient. That's what it means. And for our purpose, the last thing I would say is the probability density function of maximum likelihood estimate as n tends to infinity approaches. Any idea on to which distribution it approaches? Gaussian distribution. Approaches the Gaussian distribution with mean theta naught. Look at these equations here. When you have, see, initially you have product here. The moment you are considering a logarithm, this is an monotonically increasing function, you have summation of these random variables. So what does central limit theorem tell you? Your original distribution may be anything, right? But the moment your random variable is a result of summation of multiple random variables, irrespective of what the distribution of your random variables that you are summing up, when you are summing up large number of those random variables from that particular sample, what you end up with is a Gaussian distribution. Is that correct?
Yes, sir.
Right. So now look at here. Consider your theta bar as your random variable. That is nothing but a summation here of multiple random, as it is a result of summation of multiple random variables here. Natural logarithm of this, when you take this product, will become summation. So your theta bar eventually would become Gaussian distribution. That is the reason why the maximum, the PDF of ML estimate is for what? For this theta. That is, it is for this reason this is becoming a Gaussian distribution. Okay, that is a very intuitive, somewhat vague explanation for it. Next class will be the last class on Bayesian classification, where I would conclude it with a discussion on now maximum a posteriori probabilities. So now this is an ML based estimate for your parameters. You could estimate these parameters where you consider this theta also. Right now we considered as theta is a set of parameters. We haven't as such as an unknown parameter, we considered it, but we haven't considered it as a random variable. As the last statement here from the properties tells you is that for a different set of samples that you are going to draw, and you draw, let's say every time n number of samples, and you compute this, this indeed follows a distribution, Gaussian distribution there. So when that means this is a random variable, right? So when this is a random variable, then by making use of that fact, treating it as a random variable, and then bringing into this Bayes theorem that we have already discussed about, depending on this random variable can have anyway. This ML estimate PDF we are talking about. It's not that theta for every theta. As such theta, you cannot say anything, but if you are taking ML estimate, it takes a Gaussian distribution. I take back my previous statement that this theta will have a Gaussian distribution. It is not precise, it is not correct. The ML estimate, the PDF of ML estimate of theta is Gaussian distribution, but your probability of theta, for example, in your class, the mean value is not uniformly distributed. The mean value could be somewhere maybe from the probabilities of that will not, I might know that this would be, let's say 0 to 100 only. Okay, if my marks are from 0 to 100, that's what I'm giving in the class. Anything, it cannot have negative values, anything above 100 it cannot have. That is some information I have about what to expect for probability of theta. So our same is the case with variance. But right now, no such constraints are there in the current one. So if what I told you is a very trivial example, there can be more sophisticated and advanced examples also. So where you know that this your probability of your parameter a priori, if you have some knowledge about the distribution of these parameters, how can that be incorporated? That we will see in the next class. With that, we will conclude this module. And then probably from the class after that, we will switch to a new module that will be linear classifiers.